Welcome to MagNetZ. Um, so today, I'm pleased to present our speaker, Ualisson Bellon, who is coming to us from Edinburgh. And he's here today to talk to us about the stray field of magnetic minerals. What should magnetic particle signals look like under magnetic microscopy? So with that, I'm going to hand you over to Ualisson and yeah, take it from here.
Okay. So first of all, thank you so much for inviting me for this talk today, and thank you all for virtually attending to it as well. Um, as Brendan said, my name is Ualisson. I am a postdoctoral research associate at the University of Edinburgh, and the work I'm presenting here today is the collaboration of many people from different institutions. And I would like to thank them all for taking part of this as well. And this is a continuous developing work. And so today, as Brendan said, I'm going to talk a little bit about the magnetic field of particles, how they look like, and how the magnetic structure they have will dictate that. So this is a quick outline of this talk. I'm going to give you a very quick introduction, then I'm going to go a little bit about the physics of the stray fields, talking about the demagnetizing field of different domain states, how these different fields will look like when you're far away from your particles, and how dipolar or non-dipolar they look like. And I'm going to talk about some practicalities in terms of noise doing QDM measurements and why they matters. I'm going to talk a little bit about clusters of particles, how we can recognize them and if we should trust them or not. I am going to very quickly show the application of this knowledge, but it will be very shortly because this is not supposed to be the central topic of this talk. And I will also quickly update you on terms of what we're doing in terms of like the future, what we still have to sort out. So this is just, me early this morning looking for magnetic microscopy on Scopus on the Elsevier portal, just looking for all papers published from the 1960s all the way to 2026 and across all areas of knowledge. And as you can see, there has been an increasing interest within magnetic microscopy over the years, especially on the past few decades, across all areas of knowledge. And that's not different in paleomagnetism. Within paleomagnetism, we are usually concerned with microscopes that can let us know a bit more about the magnetic mineralogy of these magnetic areas in rocks, but also that would let us know what is the remnants related to them so we can directly apply it to paleomagnetic studies. In this plot that I like very much, we have here the magnetization intensity and magnetic moment and the different equipments and how accessible these moments are to these equipments. And then we can clearly see here that, our traditional cryogenic magnetometer can read most of the igneous and some of the sedimentary rocks as well. But as the magnetic moments become increasingly weak, or the particles become smaller and smaller, we require some more sensitive equipment to read them, to basically measure the magnetization. And that's possibly, for example, by using a squid microscope or a QDM, a quantum diamond microscope. I have never worked with the squid microscopes, to be honest, and I've been working with QDM for a few years now with data related to QDM. And what we do once we have the data is to work with the vertical component of the stray fields, the fields that leak out of the particles within our rocks. But we don't have the magnetic moments, we have to invert for them. So we invert for MX and Y and MZ, the components of each one of these anomalies. Then we have to analyze the results statistically. We have to know what are the limitations and the quality related to the experimental and the numerical methods that we're using. And that can be very tricky. But one thing we can do is to physically ground our interpretations by using micromagnetic modeling. So we can ask ourselves, how should different particles with different domain states look if we would be looking at them using a QDM, for that purpose. So I'm going to be entering a bit in the part of this talk that I'm going to show a little bit about mathematics. Please bear with me. I promise this would not go throughout the whole talk, but I need to show it a little bit of it so you can understand how we calculate these things. So we will understand that's not magic, it's just physics. So think about just a sphere, a particle of magnetite that's single domain, everything is oriented in one side, which is basically the red arrows right here. And let's start basics. Let's start with the magnetic flux density within that particle. So we've all seen this equation before. We have the vacuum permeability, magnetic permeability here. We have the auxiliary magnetic field, and we have the magnetization, which is basically these red arrows. And if we think about, if you remember the Gauss law, which says that the divergence of this field should be zero, which means there should be no monopoles, and we substitute that within that equation, we come up with the divergence of this field being equal to the divergence of the magnetization, which basically tell us that H can be expressed in terms of a self-demagnetizing field, which that's why it's essentially why we call it a demagnetizing field, because it's a field that's arising in response to the magnetization of the particle. And because of that, if we think that we are in the absence of electrical currents, the rotation of this field should also be zero, which means we can actually infer what is the gradient of a scalar potential function of this self-demagnetizing field outside of the particle. If we substitute this equation 6 right here in the equation 4, and we end up with this equation right here, and then we know mathematically that the divergence of the gradient of a scalar potential field is equal to the Laplacian of that potential, we end up with this equation 8, which is very key to what we're doing, because what's saying is that any internal magnetic variations will of course produce external variations in that potential field as well. So we end up with basically a way of understanding how the magnetic fields outside of that particle are dictated by the internal magnetic structure. But this structure, it's not essentially just connected to what's happening out inside of the particle, because at the surface of the particles, there's something happening as well. Because we have a finite element body, and because the magnetization abruptly changes from not having a magnetization, from having a magnetization to not having a magnetization at all, we form charges on the surface of these particles. And we can actually infer what is the surface magnetic charge density in any R apostrophe point within this surface by basically dictating, and basically the magnetization dictates that. So we end up in two equations, one of them describing how the potential fields outside of this particle is basically guided by the internal magnetic structure, and the other one, how it is guided by what's happening on the surface. And this is exactly the negative of the Poisson electrostatic equation. So we can actually write them using green functions of the Laplacians, an equation that allows us to any observation points outside of that particle based on the internal and the surface charge potentials, fields, to calculate what is the potential outside of it. In this specific case that I'm showing you here is a single domain particle, so there is no internal variation of magnetization, so we can basically just use the surface charges for this. And this essentially means that we can then just calculate the external magnetic field or the stray field anywhere outside of it. And as you can see right here, it's a very dipolar field. You can see the fields right here, the yellow ones, contrary to the magnetization. However, we know that most particles in nature don't have regular morphologies, and they have variable domain states. So this thing that we basically can just look at the surface charges don't often apply, especially because as particles grow, they go from single domain states, as in the particle in blue here, to more complex vortex states in the case of magnetite, becoming progressively more complex. And this means essentially that for anything that's not single domain, there is an internal variation of the magnetization, and that first term of the equation actually matters. So in here you can see, for example, a sphere, and it is a single vortex structure, so all the magnetization is within this axis right here. And you can see also the stray field that's generated by that particle. And it looks very dipolar in the same way they would do with a single domain. And the reason for that, as you can see, the single domain is the red line and the vortex one is the black one. It is basically because these two different domain states, although they are very different, they all have like just a single resultant magnetization that is concentrated in the region. But if you look very closely, you can see that if you get close enough to this particle, there will be differences. So because we are interested in understanding how different they can be and how complex the fields can look like under the microscope, we studied this in a paper that we published a couple of months ago in Solid Earth, in which we got this data that came from a rock that we did tomography to understand basically what are the magnetic minerals inside. In here you can see this is 20 microns from one side to the other, and you can see that all of the white spots appearing right here are magnetite. And once we finished the tomography and we separated the magnetic particles in it and we have the morphologies, we could then micromagnetic model their behavior. In here, for example, you have a single domain particle. In here, you have a single vortex. In here, you have like a single vortex, but more twisted, banana-like shape. And in the same paper, we calculated what was the relaxation time for each one of these particles and separated only those that were like stable at 20 degrees Celsius. As you can see here, this is the energy barriers, all the energy barriers that we have. And in here is the age of the solar system. So we just got all the data that was basically on this side of the plot. And once we have this, we have particles that are stable magnetically, and they have real morphologies, and they have a real physically realistic domain states. And then we can then go to the next step and ask ourselves how dipolar and how non-dipolar these particles look as you get closer or far away from the surface that you would be measuring this. So in here we have a first example. We have this near-micron particle. It has 770 nanometers. It is a multivortex structure, so you can see clearly, this different structure cores in each part of these two big lobes. And in here, we're not inducing any noise. We're just taking and looking at the data. If the data was perfect, then we could look at that with no noise at all. And you can see that as we get farther and farther away, the stray field produced by this particle starts very non-dipolar, but looks dipolar as you go far and far away from it. The same thing happens when the particles are smaller. So this is a single vortex one. It has 230 nanometers in this case, a single vortex structure. And in the same way, it becomes progressively more dipolar-like. We can also look at this if you look at the strength of the fields. So in here in X, you have the distance, so how far away I'm measuring the field of these particles. And then in X, you have the intensity of that field, the magnitude of it. And then you can see that the different markers with different colors are particles with different sizes, going from 30 nanometers to 1.3 micrometers. And then you can see just by looking at the behavior of them that like at short distances, they all kind of look a bit bent. And that's essentially because you have stronger contributions of non-dipolar signatures here. But that essentially after a while, they become progressively more dipolar. And then if you fit this equation right here, L should be 1 for a dipole, 2 should be, L should be 2 for a quadrupole, 3 for an octopole, and so on and on. And as you can see here, as you get farther and farther away, they get closer and closer to 3 because you're adding 1 right here. And this distance, of course, will change depending on the particle shape, the particle morphology, but it progressively becomes more and more dipolar. The other way of looking at this is basically just fitting models, right? You can just try to fit a dipolar model or a multipole model. In a multipole model in here, we are considering dipole, quadrupole, and octopolar components. So we're not just fitting everything that there is in terms of spherical harmonics, we're just like truncating it up into octopole components. So if we invert for the magnetic moments associated with these particles in different distances, so we're going to get mx and y and mz, and we know what is the true magnetic moment because these are synthetical examples. We can evaluate how good the fit is and how well our models explain the data by looking at the angular misfit, which means the what is the angle between the inverted and the true moment, or the amplitude misfit, which means like what is the difference in the intensity of these two inverted moments. So let's go to a few results now. In here, I'm firstly show the angular misfit, which again is the angular distance between the inverted and the true magnetic moment. In the left side of the panel, you have the inversion for multipolar model, and in the right one, you have it for a dipole-only model. In the x-axis, you've got the distance, again, how far away you're getting from your sample. And in the y, you've got, of course, the angular misfit. The different markers here are different particles in the same way as in the other plot. And the size of it is basically the R squared, telling like how well our mathematical models are predicting this. So let's first talk about the multipolar fit. So what we can see here right away is that in this situation where we have no noise, when you get really close to the particle, like 0.5 microns, for the biggest particles, the models don't predict well the behavior of the stray field, even for a multipolar fit. And that's because the field is so complex that we probably need more than just up to an octopolar component to represent it. But for the smaller particles, for example, the ones here, which are single domain 30 nanometers and 230 single vortex, you basically decrease the angular misfit much, much quicker than the big ones because it becomes dipolar quicker. When you compare it to the dipole fitting model only, you can see it's more stable because this is just like a linear fitting and this is a non-linear one. So that's why we've got this, spurious result sometimes right here. But the thing is, the dipolar component, the multipolar component seems to fit better to close the distance. It reaches lower angular misfits quicker than the dipolar one. But still, once you are around 5 microns, so here's 5 microns for the multipole, here is 5 microns for the dipole fit only, they both, fit the anomalies, fit the magnetic moments quite well. When you look at the amplitude misfit, this basically is repeatable with the multipolar fit, fitting better to the more complex anomalies when you get closer to your sample than the dipole one. But as long as you're a bit far away, the dipole does a good job as well. And that shouldn't be a surprise because when you look at basically in this function, this plot is a bit complicated, but I'll go through it with you. This is basically looking at the power spectra of the spherical harmonics coefficients as a distance of size, as a function of distance. So in here you have the plots for spheres, prolates, and oblates and euhedral particles. So these are the smallest particles with basically 50 nanometers, and this one has a micron. So the size is increasing as you go down in the diagrams within the same types of particles. And then in the X, you have the different degrees of the spherical harmonics. And then in Y, you get the height. And you can see, of course, that most of the energy in all of these cases is always, of course, associated with, the first degrees of the spherical harmonics associated with the dipolar component. And in all cases, past 1 or 2 microns, except for the large oblate particles, which you need at least more than 5 microns, the dipolar component dominates the energy spectrum. So this is this is actually expected, but it's interesting to show this actually for real particles with real domain states. So the first part of this talk, we can basically understand that the magnetic anomaly of individual stable sources, single domain, single vortex, and near micron multi-vortex rapidly become dipolar as you take your probe away of your sample. However, as we know, the real life is a bit more complicated, and we have noise in real life. So once you're doing experiments with the QDM, we have different protocols to try to acquire data that has viscous or not viscous components. And in reality, as you can see in this viscosity map right here, we can that this anomaly right here was removed because after doing the treatment that Michael Volk and collaborators developed, you can in theory remove the viscosity and the induced magnetization from your data and just leave the remnants. However, we know from experimental data, and here we're quoting, for example, Haas and collaborators 2024 from this same data that it was acquired in Harvard, that there is a background field of around 400 nanotesla. And on top of that background field that's constant, we also have noise. And this noise is spatially correlated, it is spectrally colored, and which means that basically the neighboring pixels are statistically related and the noise has a different power at different spatial wavelengths. So basically, to try to simulate this, we impose two standard deviations values for the noise, one at 5 and the other one at 50 nanotesla. And then you can see how it looks like here. So it's centered in 400 in this case. And then you can see the variations, which is the noise in blue and red. We added that to the data that we had. So in here, you can see that same example, and you can see how quickly buried in the background and noise it becomes as you get far away from it. So in here, for this 200 nanometer particle in 5 microns, it is barely detectable. And this for 1 micron particle, the same thing happens, but of course it can resist a bit more because it's larger. And when we look at what the noise does to the inversion results, and that's where it gets a bit tricky, because you can see that we're no longer decreasing the misfit as we increase the distance, because as we increase the distance as well, the magnetic moment of the particles, the stray field of the moment of the particles, the stray field of the particles become progressively weaker, and the noise is there. So you basically start to misfit things, and the inclination goes from decreasing to increasing. And because you basically can't invert for them as you should anymore because of the noise. And the most important thing here as well is like how quickly single domain particles stop to be, properly inverted for. In this case, for a 15 nanotesla, a sigma of 15 nanotesla, within 0.5 microns away from it, you could barely not invert for them as well, not in a good way at least. And the other thing that you can see is that you basically lose the advantage of doing a multipolar fit because in this single particle anomalies, because you're basically fitting noise in the higher degree spherical harmonic degree components. And so essentially a dipolar fit works just fine, just well. The same thing happens with intensity. So it just one is mimicking the other. And the take-home message of this is that most of the single particle anomalies on the stable geological record, which means single domain, single vortex, and multi-vortex near the 1 micron size, they should be strongly dipolar if they are coming from a single particle. Because most of the times we're measuring, the height we're measuring, it's a couple of microns away from the sample surface. And your particles are not going to be all on the surface, they're going to be also in depth. So if you're looking at anomalies, they are like coming from single sources, they should be strongly dipolar. The other thing is that small single vortex and single domain particles, they tend to be attenuated very rapidly. So the reliable observation heights should be very, very close to the sample for small, intensity of noises. But if the noise increases just a bit, it can be even worse. And the larger single vortex and multi-vortex particles can still be detected if you can mediate noise up to 5 and 10 microns away from it. But the moment, fidelity can be, significantly reduced. And finally, that dipole-only models work quite well in most traditional standoff distances because noise contaminates most of the non-dipolar signals. But the thing is, we do observe in several of our data non-dipolar signals. So where are they coming from? Well, if we know that there's more single domain particles and vortex state particles should be looking pretty much dipolar from the heights that we're measuring. So we still have clusters of particles, right? And in this data set that we simulated also three types of clusters of particles. One of them is a non-interacting with single domain, single vortex, and multi-vortex clusters. So here we have a voxel with 1 micron and 5 particles inside of it. Each one of these particles with different domain states. And then you can see the stray fields generated by these particles exactly at this surface if they were by themselves, if the other particles were not there. But once you combine them together at 0.1 microns, 1.14, and 3.23 microns, you can see how very easily they will become a dipolar anomaly as well, even though they're coming from different particles. So one single voxel can produce a dipolar anomaly as well. Well, we try to invert for the magnetization of that voxel, for the magnetic moment related to that voxel, which means for the resultant of it, we can see that in here in the stereogram, you can see the different directions of each one of the particles here. And then the star is the resultant. And then the spheres is basically the inversion as we increase the distance. So it starts to become more and more dipolar, and the inversion basically goes and walks towards the resultant direction of this voxel. But in terms of the intensity, we see that we might not actually be that close. We are close, but might not be exactly the resultant of that moment of that voxel, because you can get bias towards the big particles. The other case that we also simulated was by basically looking at strongly interacting demagnetized SD cluster. You could have this, for example, when you have a system with particles strongly interacting, and then because of that interaction, the bias field, the external bias field, could not induce any bias at all. So when you're close enough to them, they look very much non-dipolar. But as you're far away from it, it still looks dipolar, and this is basically a random direction, is not pointing towards your field just because the interaction was really strong. So yeah, it can still look dipolar, and it doesn't mean it is a stable particle. And you can have the third case in which you have TRMs, a single domain cluster that has a TRM direction in it. And when you close enough, they all look like individual anomalies. But as you go far away from it, just 2.2 microns away from it, it looks very, very, very much non-dipolar, although it's coming from single domain particles. But the anomalies, the magnitude, they decrease so quickly and they become so buried in noise that, I mean, how would you possibly fit anything in here? And from this, basically contribution of several single domain particles, and saying that, you actually are sure that you're not fitting noise here as well. So we understood that from the QDM practicalities that if you have the signal coming from a stable particle that's just an individual, most of them, maybe not all of them, I'm not going to put myself at risk here, but most of them should be dipolar if they're coming from single domain, single vortex, or multi-vortex, and you're not touching your sample with your sensor. The anomalies of the cluster, they can also look dipolar. Anomalies coming from clusters of particles can also look dipolar under magnetic microscopy. And if they're coming from clusters, they are not interacting strongly, it can actually be really good magnetic records as well. These anomalies can behave as good magnetic records as well. But if you have interacting clusters, they might look dipolar and they might not be aligned at all. And of course, if you have clusters of particles that do not look dipolar at all, they might be all over the place and be very messy. They be coming from measuring the particles really close to the surface, and you have lots and lots of particles all interacting, or they can come from large multi-domain particles, as they show in this photo, in this picture right here, with these two big magnetite grains generating this big non-dipolar anomaly, and also the same thing right here. So very quickly showing a catch-up that, relying on the dipolar anomaly sources only might not be that much of a bad thing. We just got a paper accepted on Communications Earth Environment in which we performed a full pseudo protocol from QDM anomalies in the ceramic samples, in which we took these archaeological ceramics, we did the thin section and performed the magnetic microscopy, got the anomalies and inverted for them in a full pseudo protocol. And then we compared that to the whole thing section on a 2G rock magnetometer and compared them. And I'm just going to quickly show you some results right here. You can see here in this map, several different types of anomalies. And then we inverted for all of them. And you can see the inversion results for all of them in these two stereograms right here. The red is basically the cumulative vector or the resultant of all these anomalies combined. And the star is the Fisher mean. And you can see that once we filter only for the things that our dipolar models can fit, so R squared greater than 0.9, and coercivity is smaller than 150 millitesla as well, because we only wanted things that our protocol, which is a pseudothelier, would actually act on. They basically get directions really close to what we measured for the whole thing section in 2G rock magnetometer. For the whole protocol, you can see the same thing in here. This is for the whole sample, and then you have the demagnetization, proceeding. You can see the AF field colored by from blue to red right here. This is for the whole sample, and this is what we inverted for specific anomalies in the QDM. The same thing for the ARM acquisition and for the whole sample, and here for the QDM. From that, we've basically built a demagnetizing of the ARM curve, of the NRM curve here, and the ARM acquisition curve. We plotted the pseudothelier plot of the data that we got from here, and then we linearly fitted the most linear path of it. And in here, you can basically see very quickly the result. In blue is the pseudothelier for the whole sample, in which you would get in a 2G. In green is the thelier of a classical thelier of this sample, which we believe is the ground truth for this, what was supposed to be the absolute palaeointensity. And our points right here is basically coming from the QDM protocol that we did, and we just increasing our quality criteria in a way that 0.9, we're just getting the things they are really just dipolar anomaly, and how close they get to the actual measurements using the thelier experiment. Finally, for the future, the things that we still have to sort out is how to increase the spatial resolution of the QDM microscopy. Up until a few months ago, it used to be a micron or a bit more than a micron, and we need much, much more if you want to see the smaller things with detail. But I've heard that Utrecht now, they're getting to much smaller resolutions, up to 0.6 microns. So we need to keep improving that. The other thing, we need to characterize and mitigate as much as possible QDM noise. So measuring this to understand how it changes with different temperatures, different rocks, and different heights as well, to understand what are the limitations for when we're inverting for this, how much can we trust in non-dipolar things that we are fitting, and developing clear strategies for the uncertainty propagation and error analysis as well, as we go from synthetic examples to real geological applications. And that's it. Yeah, thank you very much.
Thank you, Ualisson. I just think everyone should give a special round of applause for that talk. Yeah, it was very interesting.
Should I stop sharing?
You just got to the end of your slideshow, but I think you're still sharing, but you may want to keep sharing.
Okay.
If anyone has any questions, I think you've now stopped sharing.
All right.
Just either raise your hand or ask a question in the chat. So there is a hand from Richard Harrison.
Hi. Thanks,
Hi,
Ualisson.
Rich.
Great talk. Yeah, it was just interesting. So you showed this very nice, successful example of a QDM study and getting close to the tele. So what was the key characteristic of that sample that you think made it work? Was it the sources were well spaced out?
Oh, that definitely helps. Like, absolutely. I mean, it's no way of like, pretending that, this with this sample, like the sources were all very well separated. It was very easy to pick each one of to detect the anomalies and invert for them. And then of course, once you have everything, overlain and like lots of interactions, it will get very complicated. But Gelson, I mean, I'm not going to put words in his mouth or anything, but we should be submitting another paper soon in which this was tested for basalts as well. And of course, when you get a basalt, it gets more complicated, you get more like interacting anomalies. But the thing is, if you get enough anomalies, you should still be able to do it. Um, um, it will always depend on like, of course, like, I know you work with lots of like meteorites, and when you go to the cloudy zones and you're trying to like differentiate, what is an anomaly, what isn't. I'm not sure how well this works and the limitations of it. But for this example that I've shown you for the archaeological sample, it was a very ideal thing because we had the lots of anomalies and they were all very well separated, most of them. But Gelson is doing a full Thélier is with heating, and he has induced an artificial TRM, and then we can show that we can still recover it as long as you have enough sources. So, I mean, I think there is a huge potential to work with like all different types of rocks, but I mean, it won't be magic. It will be just, having enough sources, not having, very, very, very strong interactions, or I mean, at least with what we have now in terms of methods to be able to resolve for them.
Okay, thanks.
Yeah, thank you.
I've got another hand raised by Alexei.
Yeah, thank you. It's a great talk, and I have a two-part question, if it's possible. The first part is about the tool, the QDM tool. I never worked with it, and if it's possible, just to talk a little bit. I knew the theory, but can you tell a little bit more about the using the tool, how it works, because you tell us a few words about the resolution of the method, but if it's possible, a little bit more about the method. And the second part is about how applicable your results with the other method of microscopy, for example, with magnetic force microscopy. Thank you.
Yeah, no worries. So the QDM is basically, well, it's a magnetic microscope, of course, and the reason why it's called quantum diamond microscope, it's because you have this diamond in which we have a nitrogen vacancy, and then they form a quantum pair state in a way that once we shine a laser in it, the red fluorescence that emits interacts with the magnetic fields of the sample you have. And then there is a whole mathematical part that I'm not going to explain you just by telling you this, but you can basically measure the magnetic field produced by your sample by basically having this diamond chip with a nitrogen vacancy on top of your sample. So what it's basically doing is measuring this in the 1-1 direction of your diamond, but then we basically rotate it to the vertical direction, to the BZ direction. And what it means in terms of, in practical terms, is that you can just have any sample under it, and then you're going to basically be able to map the vertical component of the magnetic field on top of that. And what else? Is a very sensitive equipment. I am not sure if its sensitivity is greater than a squid microscope, I think it might be very close or, similar. I'm not going to put, I'm not going to, make a competition between both methods in here. But the good thing about the QGM is that you have a spatial resolution, right? So we basically, in this case, as I was saying, we have like near most of the time, like around a micron each pixel. So you can basically go around, not go around because it's not a scanning microscope, but you can basically measure this in a given area. And you're going to have spatially resolved magnetic field within your thin section, for example, which means that you also have the potential to pair this with all the microscopic methods, like you could use, for example, for instance, just as I shown like very quickly, electron microscopy to see what is around the magnetic particles that you have on the surface. Or you can use, just classic petrography to understand what is the matrix around the particles that you have, to trying to understand if they're coming from a context of being primary magnetic minerals or not. So the potential in terms of applications is, for geosciences in a general way, I think is huge. And the second bit of your question that you asked was about the different types of microscopes, like of magnetic force. Yeah. So, I mean, correct me if I'm wrong, but in this case, in the QGM, like we're getting the remnants in here because we have two induced field states. So we do it in one side and we do it in the other. And once we get the difference between them, actually, when we add them together and divide them, we get the remnant state. But in the magnetic force, you're getting an induced field moment, right? I'm not really sure. I'm not a specialist in magnetic force microscopy at all. But the difference in here with the QDM is that we're looking at the magnetic field basically generated by the remnants. In the same other ways, for example, when you have electron holography, you'll be looking at induced field states, induced field remnant. You would be looking at the induced magnetizations that the electron holography is causing in your sample. The other types of microscopes that can look at remnants, there are, well, not many of them, squid microscopes, of course, but also, as Richard Harrison has been trying to do, has been done actually, and been developing this very nicely with tachography, just doing full 3D magnetic tomography using tachography. But yeah, I don't know if I anyhow responded your question or got any close to what you wanted to know.
Thank you for your answer. It's a lot of interesting information. And just a quick question: Is it take a long time to take one picture in QDM? For example,
well, it would
millimeter to
it would
millimeter.
depend, of course, like how much you want to be affected by noise or not. Because, of course, the longer you measure, you decrease this signal to noise ratio. So for each of these maps that I've shown you, it was about 50 minutes to like 1.5 hours, depending on like how noisy it was, how quick it was. Also, as you demagnetize your sample, the anomalies get weaker and weaker. So you might want to increase your measuring time. But the thing is, it takes as much time, I guess, as doing a classical paleomagnetic experiment, in terms of, like, in this case, when you're doing a classical experiment, you take time because you're measuring lots of samples. In this case, you have lots of samples because each one of these anomalies is a sample, if you think about it, but it takes a longer time to measure it. Yeah.
Thank you for your question. It's a great talk.
Yeah.
Thank you.
Yeah, no worries.
All right. Okay. Rich has another question. I'll let you jump in there.
Yeah, sorry. Yeah, I wanted to ask about the strongly interacting clusters, because, as you know, we're sort of interested in things like framboids in meteorites, which are exactly what that models. And I couldn't quite understand nature of the problem that you were trying to say. So you can see a dipolar field in the QDM and you fit that. So is the issue that dipolar field and the moment that you invert is incorrect relative to the net magnetization of that framboid? Because everything won't exactly cancel out. There'll be some net magnetization. So is it that inversion is incorrect, or you think you should just best avoid strongly interacting grains from a paleomagnetic perspective anyway? Is that?
Yeah. Thank you for your question. So of course, like when you're really close to that sample and to that cluster, it looks very non-dipolar, right? So unless you're willing to just like fit 30 degrees of spherical harmonics to say that you were like correctly inverting for that, and even so, like with the noise, you're not really sure if when to truncate your inversion, where to stop it. But as you go far away, when it gets to become more dipolar, I was able to invert for the magnetic moment the resulting net remnants of that cluster. But the thing is, what I meant by like you're not sure about what you're looking at is the fact that it looks dipolar. You are inverting correctly for that. Your magnetic moment is correctly inverted. That's what I mean. You're reproducing the signal you're seeing, but that anomaly might not be aligned at all. It might not be biased at all towards the field because it's so interacting that it might, when you look at like everything touching and you might think about the energy barriers. I don't want to go too deeply into that because there's like a huge discussion in that as well. But like if you look at the energy barrier in terms of like everything is interacting, and then you think about, which domain state that's going to be assumed in terms of like following the nearest anisotropy axis. If everything is interacting, you need stronger and stronger bias fields to actually make the highly interacting cluster to get closer to the
right. So I see your point. But if you were to do that process for like 100 different framboids in the same meteorite, I mean,
you probably would get something. Yeah,
you would then.
But
individual one, just like any individual particle, is never aligned with the field. But if you measure enough of it, you'll get it. Okay.
But that's the point. Like the point I wanted to say with it is like this is not coming from one particle. It's coming from several. So there should be, if you think about that first example of the cluster that I showed, they're like a non-interacting cluster, which means just like they're very close to each other. That's being biased towards the field because basically each one of them will be aligning closer to the anisotropy axis. And then therefore, when you take the resultant of each one of them, it's closer to the applied field. But if you do that with a highly interacting cluster, just for example, one, like we saw that, you might not be close at all. And it still is going to be looking like a dipolar anomaly. And you're going to be like, oh, great. Is it brilliant thing?
I get it. Thank you.
Cheers.
Okay. I think that probably puts us at the end of our time for questions. I just have a short announcement. So let's thank Ualisson again for his talk.
Thank you for inviting.
And just to let everyone know, we potentially will have another meeting in 2 weeks' time. It's not yet confirmed, but you'll get the email about that if you're on the mailing list. And if you aren't able to make that or any of our other meetings, be sure to go onto the MagNetZ YouTube where this and other meetings will be uploaded. We have hundreds of presentations now available to view, so feel free to do that. And with that, that's kind of the recorded formal part of the meeting over, and we can just have an informal catch up with more questions if people would like.